In this video, I'll be going through the Titanic practice exam solution. To start, I will want to read through the project statement from beginning to end. On your real exam, they will give this to you printed out, and you will be able to read it over quickly before starting the timer. If they don't give this to you when you get to Prometric, ask for it. These first paragraphs will provide instructions on how you should submit the document and write the report. The business problem is as follows. You are an actuary in charge of expanding your company's market for life insurance. Your chief actuary wants to launch a niche product targeting people who go on luxury cruises. To better understand the type of customers that are likely to purchase, you have been tasked with conducting market research based on historical records from people who traveled on the Titanic. This product will be called Life Jacket and will provide short-term insurance during cruises. Your chief actuary wants to understand what factors contribute to a person surviving in the event of an oceanic catastrophe such as occurred on the Titanic. Your assistant has already gone through and conducted preliminary work to remove missing values, re-level factor variables, split the data into training and test, binarize factor variables, and set up code for building models. Next are the specific tasks. I will want to read through and note the number of points for each task, as well as the general type of questions that I can expect. This will help me as I allocate my time to each question, so that I will not get to the end of the exam only to realize that I don't have enough time to finish all of the tasks and still write an executive summary. The first three tasks I can see are related to the data. This is typical. Most exams begin by asking such questions. Then there's a question about k-means, a question about variable selection, a random forest, follow-up questions related to the random forest, logistic regression, interpreting the logistic regression, some model validation, an elastic net, comparing different models together, and finally an executive summary. I also want to see the data dictionary. This tells me what types of data I can expect. I can see that the level of detail is at the passenger level. That is, each row in the data represents one passenger. They also have information regarding whether they survived or not, the ticket class, the name, the sex, age, number of siblings, number of parents or children, the number fare, the cost of the ticket, and the port that they embarked from. Next, I'll go over and open up the R template as well as the solution template. Now in this video, the solution has already been completed. So when you are following along, you will actually see your solution. To follow along with this video, you can download the solution and run the code along with the video. This initial code has no changes that are needed. Simply loading the R libraries and running some miscellaneous tasks. Now let's go and look at the project statement for task 1. Task 1. Explore the survival rates by sex, p-class, and Embark. Apply a transform to fare if necessary. Now, I note that there's another code block right here. This is only part of the solution. This is showing you how the fake outliers were generated in the the question on k-means. So you don't need to understand what this is doing until we get to the k-means question. Here is code which will automatically convert all of the character variables to factors which have the most observations. Now, on the real exam, this will be given to you as well. I don't need to do anything besides running the code chunk. And next, here is task 1, exploring the survival rates by P-class, Sex, and Embark. So I first want to look at a glimpse of the data. I can see that there are 906 observations and there are 11 variables. I also look at the types of values. For instance, I can see that name has the name of the person. I can also see the type of data. See, name is a character variable, whereas something like embarked here is actually a factor. Then there's code in order to show you various statistical summaries. This table shows you that overall, 40% of the passengers survived and 60% of the passengers died. I will want to use this information as I'm typing up the solution. So I will include the number of passengers who survived and died. I'll also note the number of variables and any other information on the data that I think will be relevant. Then I look at the different summary statistics and find patterns. First, I note that passengers in higher classes, class 1 and 2, survived more often than those in lower classes. I can see this here by the customer's class. The survival rate for first class is 64%, whereas the other two classes are 48% and 24%. The saying, women and children first, applies here, as 74% of women survived as opposed to only 20% of men. Here I can see that is the case just by looking at the table. Most passengers embarked from Southampton, as you can see by looking at the embarked table. By looking at the histograms, I can identify which variables are skewed, as well as look for potential outliers or other abnormalities. For instance, in the age variable, I note that there is a very high number of passengers who have a specific age of 30. I thought this was odd, and so I made a note of it. While the mean is 85, the max, there's also a lot of skewness in the distribution of fair. So let's look over. So here's the distribution of fair, which you can see is highly skewed. And there's a spike at about age of 30. So I'll go through each of the histograms and make notes of anything that is out of the ordinary. Typically, there'll be a few questions, a few abnormalities that they will expect you to find. Finally, if the variables are right skewed, such as in the case of fair, you will want to apply a log transform. Task 2. Create a new variable called title, which captures passenger's title, such as Mr., Mrs., Doctor, and so forth. So I will first want to see what template code they provide. And for this question, I first need to look at the original title. So I run these 2 lines of code, and I can see that there are a number of different titles. There's Captain, Colonel, Don, Doctor, and so forth. Now you can look here and see that there are only a few passengers who have some of these titles. There's only one passenger that has the Captain title, only one passenger that has the title Don, and this can create problems if you try to use this title variable in a predictive model by itself. It will result in a coefficient being added for each of these titles. However, it will only apply to that one passenger. So if you use this in a model, it will make the model very unstable. The p-values, if you're using a GLM, are determined in part by the number of observations which are for each factor. In other words, the p-values for each of these titles with only one observation will be very large. So to fix this, we want to convert the titles to a much simpler format. We want to say that Miss or MLLE or MS or MS all mean Miss, MISS. Likewise, officer, captain, colonel, major, doctor all refer to officer. And next, I will look at the count and see that there are now fewer titles and more observations in each title, which is what I expect to see. Task 3, create a new variable called family size, which counts the number of family members that a passenger has on board, including themselves. So here I want to create a new variable, and I want to look at the data dictionary first of all. So I note that there's nothing here that says family besides SIB-SP, which is the number of siblings, and PARCH, which is the number of parents or children. So I want to add the number of siblings plus the number of parents or children plus 1 for that passenger themselves. And I'll call that variable family size. If I didn't want to use the pipe operator, I could say df family size is equal to df SIB plus df PARCH plus 1. Task 4. Use k-means to detect outliers. Some of the data from the Titanic was of questionable quality. Some people had missing data filled in after the ship had sunk by contacting relatives, looking at social security records, tax info, and other public records. We don't trust this data, and we want to exclude it. We only know that this impacted between 5 to 20 passengers for the variables age, fare, P-class, and family size. One use of clustering algorithms is for detecting outliers. If a passenger has a very high or very low value for certain variables, then they are dissimilar to the other passengers, and they will be put into a cluster by themselves or with others who have similar values. Put each passenger into a cluster using k-means. If a cluster has fewer than 5 passengers, then say everyone in that cluster is an outlier. There should be anywhere from 5 to 20 passengers that are classified as outliers. Choose values for the number of centers, k, and the number of starting values, end start, and justify these choices based on the data set and the goal of detecting these outliers. Any cluster with fewer than 10 passengers in it should be counted as an outlier cluster. Once you assign clusters, create a new column called outlier flag, which identifies these passengers. Then remove the cluster feature, aka the cluster number column. That's a lot of instructions. So let's go and look at the code that they give to us. Here I can see that they provide quite a lot of code. And this is when it's very important to follow the instructions closely, because it's easy to make a change that will have unexpected results. So first of all, I can see that they are setting the random seed. This ensures that the random numbers that are used to cluster are repeatable. In other words, if you run this report multiple times, you will always get the same results, assuming that the random seed is the same. Then I can see that they're creating cluster data. Now I can see that they're also doing some other complex data stuff, but I don't need to know what that's doing. I just need to know that it's called cluster data. And here I'm getting an error because it's saying family size is not found. Now what this means is that I haven't run this chunk of code here. So I'll go back and run this. Okay. Now I can actually see, if I look in the R environment up here, I can see this cluster data object, which was just created. If I was very curious, I could even click on this object, and I could see that there is an age column, a fair column, a p-class, and a family size. That's useful. Next, I can see that there is this run k-means function. Now, I can assume, without even understanding the code, that run k-means is going to run a k-means algorithm. It's going to take two arguments, centers and end start. If I go back to my question here, I can see that they give us this information. They say put each passenger into a cluster using k-means. If a cluster has fewer than 5 passengers, and say everyone in that cluster is an outlier, there should be anywhere from 5 to 20 passengers. Choose values for the number of centers, k, and the number of starting values, n start. So here you can see that these are the two values which I need to choose. And then I can see that there is a run 1, which is equal to the result of run k-means with 10 centers and 3 starts. If I just run this and then look at the result, I can see that there is a cluster number, an n, which is the number of passengers which are in each cluster. If I change the number, now first let's review what k-means does. K-means tries to split up the data into a given number of centers. So if you say that k is equal to 10, it will try to divide up all of the passengers into 10 groups such that each group is as different as possible. Now, difference means that they have different age values, different gender values, different fare values, different types of tickets, and so forth. So let's just look at two examples. Let's say that I used a really high number of centers. Let's say I used 100 centers. Then each center would only have a few passengers in it. And so, um, and so each center would only have a few passengers in it. Each cluster would only have a few passengers in it. However, if I use, let's say, only 2 centers, then there will be a lot of passengers in each of those centers, as follows. Now, what's interesting here is that when I use 2 centers, I get 888 passengers that all get put into one group, and then there are 18 who are off by themselves. So just by looking at the counts here, we can hypothesize that these 18 passengers are outliers because they're very different from the other passengers. Now, I can keep going, and I can read what the comments say. It says, select the k-means run to use. So this could be, either run 1, run 2, or run 3, or I could even try out a different value. Like, let's say I wanted to try out 5 centers, and I also wanted to use 50 starting values. I'll name this run 4. I could look at the counts here and see that there's a wider distribution. Most passengers go into the 5th cluster, but there is also some other clusters which have a fair number. So first I have to select the k-means run to use. And then I select the cluster which you are counting as outliers. So let's say that I wanted to use this cluster here, run number 4. And let's say I think this cluster 1 are outliers. So I'll say this is run 4, and this is cluster number 1, which are the outlier clusters. Now I could also say that it might be cluster 1 and cluster 2, which are outliers. So I would just say 1 and 2. And then I just add the selected cluster assignment to the data. And next I can visualize what these will look like. So I can see here that there are 1, 2, 3, 4, 5 different groups. And I can see what the variables look like across age, p-class, family size, and fare. I can see that there are some general groups, but the colors here do not match the segment of points. Like right here, you can see age and fare. See that all of these group points, all of these passengers are in one big group, and yet they're being divided up based on color, which doesn't make sense. So let's try run number 3. Let's go back and look at these counts. Okay, and now I see that there are 3 clusters, and let's just try out cluster number 3. If I run this code, I can now see that there are really 2 groups here in this big chunk of passengers. There's a green cluster and a red cluster, and then the blues here. Now this next line of code will filter to only the outliers or non-outliers. So here the green and the red represent these 2 groups, clusters 1 and clusters 2. And the blue represent cluster 3, the 18 passengers that I'm expecting are outliers. And here this looks like a very appropriate choice because all of these passengers get grouped together, but then there are some outliers here. So going back to the beginning of this solutions file, this is how the data was actually generated. And this is how the SOA might generate fake data on a real exam. They specify some fake passengers. They give them a fake passenger ID. They give them a random survived status, a random customer class, and so forth. However, they choose the values to be extreme. So the age here, the age is being sampled from either age 1, which would be an infant, age 100, which would be an old person, age 105 or 97, or even age 0. And you can see that by doing something like this, they could add in fake outliers and then have a precise answer. The precise answer is that there are 15 outliers. So when I'm writing this up in the report, I will first want to explain what the algorithm is that I'm using. So I would say something like, K-means is an unsupervised learning algorithm that seeks to partition the data into homogeneous groups based on numeric variables. By minimizing the sum of variances, the squared Euclidean distances, within each cluster, group of observations known as clusters are created. In this context, we assume that the people who have missing values filled in will be dissimilar to everyone else so that they will be in their own cluster. Because this is such a small data set with fewer than 1,000 observations, we should use a higher number of starting iterations and start. So I set this to be 50. This just means that the k-means algorithm is actually run 50 times, and then the cluster centers are taken as the average of each of those cluster centers. Now this is very simple. It means, like, let's say you run k-means once, and the first center is a vector that says age is equal to 2 and fair is equal to 4. Or 5. That's the first cluster center, and the second cluster center has age is equal to 1, fair is equal to 3. Then if you said, okay, n start is equal to 2, because we ran this twice, so this implies that the average center would be age is equal to 1 plus 2 divided by 2. Fair is equal to 5 plus 3 divided by 2. And so you can see age is equal to, well, the average of 2 and 1, 1.5. Fair is equal to the middle point of 5 and 3, which is 4. And that's how you go from a large number of starting values down to a single group of cluster centers. And here I provide the output. It's always a good idea to include more output than you think might be necessary, especially if they give it to you for free, such as in this case. Task number 5. Select which variables should be used in modeling. Your assistant was not sure which variables to keep, and so they have included everything except passenger ID because they realized that this has no relevance as to whether or not a person survived. Decide on which variables will be useful for predicting survival and delete the others. So you might be asking, well, what if there is some useful information in passenger ID? Like perhaps passengers who purchase their tickets sooner had a lower passenger ID than those who purchased their ticket later. Could there be some information that would be useful in modeling? In theory, yes. However, they tell you that they've already removed passenger ID, and so there's no point in spending time including it. Let's look at task 5. So they say select which variable should be used in modeling. So here I want to remove passenger ID, and I also want to remove name and ticket. Why is that? Well, let's go and look at the data. The data is called DF. So there are a few ways that I can look at it. I can type view with an uppercase V, DF into the console, and bring up the whole table. Or I could also have gone to environment here and then clicked on DF. Now this gives me a complete view of the table. So here on the left, I can see that passenger ID is almost a unique value. And I can also see name. Name is almost unique. There may be some passengers which have the same name. Like there are 2 Anthony Abbings here, for instance. And there are 2 Samuel Abelsons, but even they have a different spouse. So name is basically a unique identifier. And that's not useful in a predictive model. Why not? Because if I tell you that my name is John Smith, that doesn't tell you anything really useful about whether or not I would survive a catastrophe. Now, that isn't to say that name isn't a useful variable at all. There are other possible ways that one could use name information. For example, you could look at a person's socioeconomic status based on their name. Like maybe someone who had a name from being in a royal family, for instance, or being related to a famous person would have a higher likelihood of surviving. If you didn't have family information, you could even find ways of connecting passengers together based on their name. You could do things like coming up with new features based on family size and type of family and so forth. But we don't need to do that here because we already have variables for family outlier flag. So name is really an irrelevant variable. Furthermore, there are far too many unique names. If we were to use name in a model, it would try to add a coefficient, if this was a GLM, for each name. So there would be a variable for Miss Thameen Zabur. There would be another variable for Mr. Jarius Youssef, and so forth. And this would result in a very, very unstable, unreliable model because almost no passengers have the same name. The same is true for ticket. Ticket, again, might have some useful information, but there's no way that, given our data dictionary, that we can get more detail. If I wanted to see the count of these variables here, I could say df count name I could see, okay, there are some passengers who have the same name, but most passengers don't. I could also use table df name and see the same result here. And I could do the same thing for ticket. And so forth. So to summarize, whenever you have a variable that has too many factor levels, it either has to be removed or you have to find a way of simplifying the factor levels down. So here I remove these high cardinality features. That's the fancy name for them. And then I want to collect these variables to create dummy columns, dummy variables. And again, if I want to see what this data frame is, I can look over on my environment and click on df dummies and see this has just created indicator columns. If sex is female, it's a 1. If not, it's a 0. If embarked is C, then it's a 1 or 0, and so forth. So here you can see if I was to include like name and then run these dummy column, it would create a column for each person's name. So this matrix would be very, very wide. Task 6, fit a random forest. We have a lot of variables, but because our goal, let's go back to the project statement. Task 6, fit a random forest for variable selection. Your assistant has set up a random forest. Explain the trade-off between using AUC instead of accuracy for this problem. Explain what ntree and mtree do, and then choose reasonable values. The purpose here is just to select features, and so the values do not need to be perfect. Record the top 7 most important variables. Let's go and look at the code. They first set a random seed, and then they fit a random forest. They use 3 trees, and they use mtry equal to 300. Are these reasonable values? Well, let's look at this project statement. It says, first, explain what mtry and mtree do, and then choose reasonable values. So most often, if they ask you to make a selection for a parameter, it means that the default values are not going to be the best choices. So what I can do is look in the R documentation. I can type in $random forest. Why did I know that it was $random forest? Because right here, where it says RF is equal to random forest, and this is where I make the selection for mtry and ntree. So I know that the all of the documentation for these parameters is going to be contained in the random forest function. So here I can scroll down and I can see ntree is the number of trees to grow. This should not be set too small of a number. Well, look at this. ntree is equal to 3, and 3 is a rather small number. So I know immediately that I should increase ntree. mtry is the number of variables randomly sampled as candidates at each split. So when you fit a random forest, the idea is to make each tree different from all of the other trees. Now this helps to improve the overall model performance because the variance of each tree increases. And so when you take the average of all the trees, the variance then decreases, and it reduces the likelihood of overfitting. So one way of making the trees more random or more independent from one another is to use different variables for each tree. So you restrict the number of variables called mtry that each tree can possibly use. So in this case, you want mtry to be some value that's smaller than the number of variables that are in the data. Now, again, if you look at the dimension of the data frame, you can see that there are 16 variables, so 15 predictor variables. So you expect mtry to be some number less than 15. You can also see the default value, which is the square root of p, where p is a number of predictive variables. So if your data frame has 15 variables, a reasonable value for mtry is the square root of 15, which is about 4. So that's why I chose mtry to be equal to 4. And I wanted to set the number of trees to some higher number. So let's just see what it would have happened if I tried to fit this random forest. I can see that here I can see the number of trees on the x-axis and the error on the y-axis, and the number of trees only goes up to 3. The accuracy is 71%. The AUC is 78%. Now let's try using 200 trees and 4 mtry. Now this shows the number of trees on the x-axis, which goes up to 200, and then the error on the y-axis, which you can see continues to decrease down to about 150 to 200 trees. One nice feature about random forests is that it's very difficult to choose a number of trees that's too high. Now this is because each of the trees are basically independent of one another, and so if you use a really high number, like let's use 1,000. We'll see that the accuracy flattens out after a while. And so training random forests is relatively easy to do. So to summarize, I would be sure that I'm answering what the question's asking for. So they say, first, explain the trade-off between using AUC instead of accuracy. So AUC is often preferred for binary classification over accuracy when there are more observations in one class than in another. Now in this case, there are 260 people who survive, but 420 who die. So if we were to just use accuracy, the overall accuracy would be biased towards making good predictions for those that die, because there are more of them, but worse for those who die than those who survive. For example, if we just predicted that everyone would die, our accuracy would be 420 over the total number of records, which would be 62%. So you might say, oh, 62% accuracy, well, that's better than random guessing, right? Because random guessing would be 50% accuracy? No, that's actually wrong. Random guessing would be 62% accuracy. So that's why AUC is preferred. AUC uses a AUC balances performance on the survivors and those who die by taking the area under the receiver operator curve, which is a graph of the sensitivity versus the specificity. I just copy and paste the results from the our documentation. I also want to provide some description as to the result here. So here I include the graph, and I also note that I looked at the cross-validation error against the number of trees and found that the error continues to decrease up to about 100 or 500. The value of 300 for MTRI, which your assistant set up, does not make sense because there are only 15 predictor variables in the data, and so it's impossible for any given tree split to consider more than 15 variables. I set MTRI to 4 as a good rule of thumb as the starting value. This is the square root of the number of predictors. So whenever you make selections for a model, you should see that the performance improves over the default. Here you can see the accuracy improves from 77% to 81%, and the AUC improves from 80% to 83%. Task 7. Based on your random forest, choose the top 7 variables by importance. Note, the random forest package uses the mean increase in node impurity as importance. The other common importance measures is the increase in accuracy. So let's go and look at the code here. Okay, and I see that they calculate the importance. So first of all, I would want to explain what variable importance is. So I would say variable importance is a way of measuring how each variable impacts the model's predictions. This is a numeric measure which is between 0 and 100, where 0 means that the variable was not used at all, and 100 means that the variable is more important than any of the other variables. And in this case, they want you to provide the top 7 variables by importance. And that's what this code does. And I can see that the most important is sex, female, followed by fair, P class, and age. So I would just paste these results in to the report and keep moving. Task 8, fit a logistic regression and interpret the signs of the coefficients. What do the signs of the coefficients indicate? It is acceptable at this stage if some of the p-values are greater than 0.01. So here is code to fit a logistic regression. And I have to make selections for the variables that I want to use. I need to use survived because that's going to be the target variable. And I want to choose the variables here which are most important. So this is sex, female, P class, age, fair, title master, family size, title miss. And here I get coefficient estimates for each of these values. A logistic regression is a GLM. The response family is binary because a person can either survive or not. And so the binomial family is appropriate. The logit link is the most common link for binary classification. At first, the logit was not fitting because the variables used were linearly dependent, and so the model matrix had a zero determinant. This was because the family size variable was a linear combination of p-arch and SIP sibling. So I had to remove p-arch to fix this issue. So if you want to see what that looks like, I can just add back p-arch. And I look at the summary here. I can see I haven't include SIP sib. See here, I've included family size and p-arch, right? But that's not that's still not enough information. If I wanted to recreate the linear dependence issue, I would need to create all three. And now you can see that the coefficient here is NA on SIP sib. This is because once you know the p-arch and the family size, you can back derive the SIP sib. And so it causes an error in the GLM algorithm. This is because the model matrix is rank deficient. Task 9. Using the model's coefficients, calculate the probabilities of a person age 10, 30, or 60 surviving. For the other variables that are in the model, use the median for continuous variables and the mode for factors. You may use the predict function to check your work, but the calculations need to be shown explicitly for full credit. Using Excel may save time. To convert from the log odds to the probability, use the fact that for P, the probability of survival, Z, the linear predictor, Z is equal to P log of P divided by 1 minus P. So here, this code gets the median for continuous variables and the mode for categorical variables. So here I can see sex female is categorical, and so the mode is 0. This means that most passengers are men. The most common customer class is 3. The most common title is master. The most common title master is 0. In other words, most passengers don't have the title master, and most passengers don't have the title miss. And here I can also see the mean. So the mean fare is 2.7, and the mean family size is 1. So in Excel, I can recreate the logit model using the coefficients as well as the average passenger values here. So these coefficients I get directly from the logit model. So right here you can see sex female is 3.21, 3.1 approximately, and so forth. And then I want to add the median or the mode for each of these values. I said most passengers are male, so sex female 0. Most common customer class is 3. And then I want to test out different values of the age. So let's say age is equal to 10. Fare is the average fare, which is 2.7, and so forth. Then I can say that the linear predictor is equal to the sum product of the coefficient with the x values. And then the survival probability is the exponent of this number divided by 1 plus the exponent. So this is equal to p. So this right here is z in our formula. And this is the survival probability, p. So if I go back here, I can see z is equal to log p over 1 minus p. And so p is equal to the exponent of z over 1 plus the exponent. So I had to do some algebra there in order to solve for p. So if you solve this equation for p, you'll get p is equal to exponent z over 1 plus exponent z. And then I can do the same for age is equal to 30 and age is equal to 60. And then I can observe the change in probability. So for people of age 10, on average, the survival probability is about 7.5%. As they get older, that probability decreases. At age 30, it's 6.9%. At age 60, it's 6.1%. If you got slightly different values for the coefficients, you could simply copy your coefficient values here. Let's go back and fix these coefficients. I could simply copy these coefficient values somewhere into Excel. Oh, and here I've copied too much output, which is actually a common glitch. Let's try that again. Okay, so here are my coefficients. I just care about this part. So I'll just put this over here. And then I'll go to data, text to columns, delimited, next, space. Here I can get my estimates. And then I would just replace these values here. So I'll go paste values, and then these formulas here would just update. Here is a written summary. The logistic regression is a type of GLM which models the probability of surviving. The response family is binomial, since each passenger can either survive or not. And here are the calculations, survival probabilities. Task 10. Validate the logistic regression and compare the AUC and accuracy to the random forest in task 5. For accuracy, use cutoff of 0.5. Explain, prior to looking at the result, what you would expect given the logit is in the top 7 most important predictors. Then, compare the AUC and accuracy. What are some of the differences in model structure which may account for this discrepancy? Explain how these differences relate to the large p-values for some of the variables. So let's go to task 10. Oh, and I actually missed a step in task 9. So that calculation that we did in Excel, you can also validate by looking at in R. So this creates a table with each of these values. So this is the median age equal to 10, the median fair, and so forth. And then I first predict this person age 10. Here you can see age is equal to 10. And this is their probability, 0.07. And then I can make an adjustment and say that their age is equal to 30. Then make the prediction and see that that decreases. Again, adjust their age to 60. See that the probability of survival decreases again. Okay, so going back to task 10, validate the logistic regression. So here, this just predicts predicts which passengers will survive on the test set, and the accuracy is 78%, and the AUC is 80%. And here they say for accuracy, use a cutoff of 0.5. Now, what is a cutoff? The cutoff value is the threshold that determines if a person is predicted to be alive or dead. The result of a logit model is a probability. And so if you want to predict if someone survives or not, you have to say, is that probability greater than 0.5? If yes, then they survive. If it's not, then they die. So that's what this is doing here. It says sum of predict model greater than 0.5. If I wanted to use a different cutoff, I would just change this to a different number. What are some of the differences in model structure which may account for this discrepancy? Explain how these differences relate to the large p-values. So I would expect that the performance would be worse because the random forest has 14 variables, but the logit only has the top 7. So there's less information in. In addition, the random forest automatically captures interaction effects and nonlinear transformations, whereas the logit does not. So the random forest is taking into account the person's age, the person's gender, the person's ticket class, all at once. Whereas the logit is just saying that they are each independent of one another. It also does not detect nonlinear patterns, whereas the random forest, because it's based on decision trees, can get nonlinear patterns. What that means is that because a logit is a linear model, it assumes that continuous changes in the inputs always result in continuous changes in the prediction. So if someone's age increases from 13 to 15, that would improve that would change the survival probability by the same amount as if they changed in age from 73 to 75. But intuitively, you know that that's likely not the case. You know that there's some non-linearity in the age variable. And the decision tree, the tree-based model, does a better job of capturing those non-linearities automatically. So again, if you compare the accuracy in the AUC, you can see all of this information. You can see that the random forest has an AUC of 0.832, whereas the Logit only has an AUC of 0.830. So again, it would be very surprising if you took a Logit model with fewer variables and got better performance. It's not impossible though. Task 11, fit an elastic net with all pairwise interactions. So just as we discussed in the prior question, the Logit doesn't automatically look at interaction effects. However, there are ways that we can do that. So let's look at this code here. This is a formula that says survived is equal to dot squared, which is a cryptic way of saying that I want to use all variables and all interactions. So here you can see title Mr. As well as the interaction of sex, female, and fair, interaction of P class and fair, interaction of age and title master, interaction of fair and title miss, and so forth. So run the code to create a model matrix which has all pairwise interactions. With 7 original variables, there are 21 variables after adding the interaction terms. Set the value of alpha so that you can perform variable selection. As a bonus question, for a model with p variables, how many variables will there be after adding all pairwise interactions? So it turns out that if you, after considering all pairwise interactions, there would be p plus p choose 2 terms, where p is the number of original variables. There's a bit of combinatorics for the actuaries in the audience. So let's run the code here using this data. And this says, set the value of alpha so that you can perform variable selection. So what happens if alpha is not equal to 1? You know that if alpha is equal to 0, then you have a ridge regression model. Well, let's look at the documentation actually. Let's type in glmnet here, and let's scroll down to the parameter that we're interested in, which is alpha. So this is the elastic net mixing parameter with alpha between 0 and 1. The penalty is defined as 1 minus alpha beta L1 squared plus alpha times beta. Now, this isn't very readable, but what this says is the penalty term is 1 minus alpha times the square of the coefficients plus alpha times the absolute value of the coefficients. So what that means is, like, let's say that you fit a model and the coefficients on age was the age coefficient was equal to 2, and the fair coefficient was 4, right? And so if a person had, age is equal to, if a person was age 20, then you'd take 20 times 2 plus, let's say that their fair was equal to 100 times 4, plus some intercept term. Let's say the intercept was, I don't know, 5. Then this would be the linear predictor. The linear predictor would be the coefficient on age, which is 2 times the person's age, plus the coefficient of fair times the person's fair, plus an intercept term, right? That would be the linear predictor, which would be some number. So if you want to measure how complex the model is, you can look at either what's called the L1 norm or the L2 norm. So the L2 norm is the sum of the square of the coefficients, which in this case is 2 squared plus 4 squared. And the L1 norm is just the sum of the absolute value of the coefficients. So it's just absolute value of 2 plus absolute value of 4. Now, the theory is a little bit more complicated to explain all in this one video. But the important point from all of this is that when you say alpha is equal to 1, you get a lasso. And a lasso is important because it can remove variables entirely from the model. When a coefficient is equal to exactly 0, it means that that variable doesn't get used at all. When alpha is equal to 0, you have just the ridge penalty. So if you looked at this equation, when alpha is equal to 1, you can see this first term is 1 minus 1. So this first part goes away. Likewise, when alpha is equal to 0, the second term goes away. So when alpha is equal to 1, this part goes away, and so you just have the L1 norm, which is the lasso. When alpha is equal to 0, you have the second term disappear, and so you just have the L2 norm. So that's a very long-winded way of saying that if you want to perform variable selection, then you need to set alpha equal to 1 so that you get a lasso model. And so that's what I do. That's what is done here. Alpha is equal to 1 implies lasso. Alpha equal to 0 implies ridge. Task 12. Choose a value of lambda that results in about 5 to 10 variables remaining. Interpret the graph. Hint, look at plot GLMNet as well as the model's coefficients. So here, here I will just run the code. Don't need to make any changes. And it shows on the x-axis some numbers between -8 and -2. And on the y-axis, the binomial deviance. What is the binomial deviance? I don't know. Well, hint, type plot GLMNet. Let's type that in. Question mark plot GLMNet. Okay, so let's see. X is the fitted GLMNet model. Xvar on the x-axis, so that's the x-axis here. On the x-axis, norm plots against the L1 norm against the coefficients, lambda against the log of lambda values, deviance against the deviance. So what's the default value? Deviance. Well, so that's why this is binomial deviance, right? That's what this is doing. Oh, okay. So here on the x-axis, I see the fraction of deviance explained. And the y-axis, I see the value of the coefficients. Let's say I wanted to instead show lambda. I just changed this to lambda. So lambda is much easier to interpret because lambda is the shrinkage penalty term. So when lambda is equal to 0, you have no penalty. You just have an ordinary logit model. As lambda gets larger, there's more of a penalty for the coefficients. So the model shrinks. In other words, coefficients are getting removed. So you can see here, as lambda is getting larger, that more of the coefficients are going to 0, which means that they're getting dropped from the model. The graph below shows that the best value of log lambda is about -10, which means that lambda is about exponent of -10. This is a very small number, which results in a low penalty, and hence a complex model with many variables. So here, I wanted to choose the value of lambda so that about 5 to 10 variables remain. And here, when I say lambda is equal to exponent of -4, then you can see these coefficients are all zeros, but these ones are not. So there are 1, 2, 3, 4, 5, 6, 7, 8 variables remaining in the model, which is what we want. Task 13, compare the AUC with the Logit's AUC. So here I can see the AUC from the Logit test is 0.81. And that's not, so here we can see the Logit's AUC is about 0.83, whereas the Lasso's AUC is better. It's 0.838. Now this makes sense because the Lasso is including more variables. Remember, because we added all of the interaction terms. And so this would likely improve the model. The accuracy is also better. The accuracy is about 81 as opposed to 80. Finally, the executive summary should use non-technical language to summarize the steps that you performed. It should include a problem statement, coherent explanation of all steps 1 to 13, and insights into how these findings can help Life Jacket be a successful product. So to write the executive summary, I would simply go back to the beginning of the report and then type, go to View, split the windows up and down, and then scroll the top, the bottom window will go down to the executive summary here, where I could type So here I would be able to type, and then I would go up to each of the tasks and explain in non-technical language. It's always a good idea to start the executive summary by going back to the business problem. So here, if you see the business problem from the project statement, you can see it says you are an actuary in charge of expanding your company's market for Life Jacket, etc., etc. So I would start off by saying, in order to make the market in order to market and price this specialty life product successfully, we need to understand the risks associated with travel cruises and so forth. And there's not a single right answer. There are different ways of writing this. However, the structure should be consistent. And you can save yourself some time if you keep these structural ideas in mind. So first of all, just restate what the project statement is asking for. Then talk about the data. List the number of variables and what you're trying to predict, as well as the overall type of data. Here it's passenger information, and the variables that we have are their gender, their ticket price, and so forth. And then I move on through each task. So I started off here by task 1, where I was just describing the data. And then in task 2, I simplified the title. And then in task 3, I created the variable family size. Then I looked for potential outliers. Here I say, we found that there were 18 passengers who were very different from the others. Their fares were extremely high, and so forth. And so I just go through each of these tasks, keeping in mind that the audience is a non-technical audience. So instead of going into a lot of specifics about the random forest, I just say there were a lot of variables to consider. To simplify, we used a random forest to determine which were most predictive of survival. This is a data mining method which is easy to calibrate and provides a measure of the importance of each variable. And then I go through the Logit model. I have a paragraph that says, once we simplify the variables down to 7, we fit a Logit model. This is a type of model which takes multiple inputs at once and predicts survival probability. And then I go on to task 9. Where I say calculate the probabilities of survival. And then I validate the logistic regression, and so forth. Finally, it's good to include a conclusion paragraph. Our investigation identifies the most important risk factors for passengers on board the Titanic. Such an event is a complex process involving many people interacting over several hours, and so the goal of predicting who will survive and die is challenging. 100 years later, the safety standards of cruise ships have improved, and we would be able to extend this analysis to include recent cruise experience while applying similar statistical analysis. So it's always a good idea to try to extend the analysis to consider future research options, or to say, if we had additional data, we could try out different analysis. We could, for example, benefit from having insight from the passengers which had missing information.